I'm Simon Danucci, and I've been a safety engineer and consultant for over 20 years now. So when I decided to start my own business, I was wondering what I was going to call it. And I looked around at various names, some of which were already taken, and I came up with the name The Safety Artisan for the business and the website safetyartisan.com if you want to take a look. And I came up with that name because I liked the word artisan and what it meant and the connotations. So first of all, I mean, artisan means a skilled person who does something by hand. And it can also refer to a thing that is, specially handmade, usually with high quality materials. So I like the sound of that. And I think it's appropriate, even in this modern age where I've worked on, huge projects, multi-billion-dollar projects that lasted for years and involved thousands of people. Because even on a big project, we're still relying on individuals being competent to do a job and to know how to do it, and to have that skill and that awareness and that understanding. So that artisanship, that appealed to me. I thought that's good. And another thing was that there's this connotation of somebody working alone at home, maybe a sort of a cottage industry type setup that used to exist before the Industrial Revolution. Oh, I should say before the first Industrial Revolution. Now, whichever Industrial Revolution we're currently in at the moment, I don't know. But we've gone back to a world where, thanks to the internet, you can sit at home and do work. And in fact, thanks to, the recent global pandemic, more and more of us have been sat at home doing work, working remotely over the internet. And I, as an individual, can reach hundreds, thousands, or even millions of people over the internet with my teaching and with my knowledge and experience. So, the internet has really enabled a return to those kind of cottage industry ideals where individual people can do something of high quality and find a market for what they're doing, regardless of, big brand, big business, etc., etc. So we can, you and I can communicate one-to-one or one-to-many, and you can communicate with me, and we can learn together and share together what we want to do. Now, if that sounds good to you, if that sounds something that you're interested in, then please check out the videos and other learning products at safetyartisan.com. And you'll also find me, Simon Danucci, on udemy.com. So if you want to see what I do on a third-party platform, and then that's there too. Okay, well, thanks very much. And I look forward to seeing you again soon. Cheers. Well, that's enough of that. You get the idea. Hello, everyone, and welcome to today's webinar. Can I just check? Can you all hear me okay? Can anybody in the chat or out loud just confirm that you can hear me okay? Let me get rid of... Oh, thank you very much, John. That's terrific. Thank you. Okay, well, welcome. Today is the first in a new series of, and thank you, Rachel. Nice to see you again, as it were. Oh, great. Thank you. So that's all good. What I'm going to do then is I'm going to switch. I'm just going to share screen. And let's get this started. So hopefully you're expecting a webinar on failure modes and effects analysis. And this is, as it says, it's a webinar. We've got some how-to. We'll go through an example later. We've got some templates and tools and other goodies for you, some resources. And I've put some links in the chat already, and we'll come back to talking about those later. So that's what we're going to do for the next hour or so, and we'll have a Q&A session as well in a minute. And that's great. I can hear more and more people arriving. So welcome to the webinar, everyone. And we've got a good crowd today, which is very, very pleasing. So a quick plug, I guess. Why listen to me? Why should you be here listening to me? What do I know about anything? So as it says, my name is Simon Danucci, and I've been a system safety engineer for around 25 years now, as well as doing, other kinds of, workplace health and safety comes with the job, and other things like that. So I've done various things over the years, and I've been lucky enough to work on all kinds of systems, lots of aircraft. I did 20 years in the Air Force, so lots of aircraft, but also ships and submarines, sensors, command and control systems, air traffic management systems, a little bit of vehicles, but not much, as in sort of cars, trucks, that kind of thing, and trains, but very little of that. A bit of cybersecurity and lots of software safety. So that's me in a nutshell. Okay, that's the kind of things that I've done. And I've also been lucky to work on some very big projects, gigantic projects. Actually, maybe I've been lucky to work on small projects. Those have been nice. Some of the big ones have been hard work. But I've done a great, variety of size of projects, and I've worked, as you can probably tell from my accent, I'm from the UK. I've worked in the UK. I've worked 10 years in Australia now. I've worked on a lot of American systems, so I know the American defense way of doing things, and I've worked on some systems in the European Union. So I've got quite a varied bag of experience with which to inform what I'm saying and hopefully give you some value. So that's me. So topics for this webinar, and these topics are a guide, okay? So if you look up what are the most popular queries or searches online for FMEA, failure modes, effects analysis, these are the topics that you will get, okay? So what FMEA stands for, who invented it, what it can be used for, when it should be applied, where it is used, why it's important, and some stuff about tools. And then finally, how FMEA is done, okay? And as I say, we'll have a Q&A session, and then I'll go through a very simple worked example, okay? So let's move on then to our first topic. So FMEA. So I liked the way, I think this is the American Society for Quality or Australian Society for Quality, I can't remember. I like the way they put it. So we're talking about two things: failure modes, different ways in which something might fail. Okay. And it says, yeah, any errors or defects. I says affect the customer, the end user, whoever is using the item, let's say. And I say item, it might be a physical thing or it might be a process. FMEA is very, very widely applied, as we will see.
And the failures might be, it says potential, okay, they might never happen, or they might happen and nobody notices, or they might be significant. We'll see. And then effects analysis, well, what are the consequences of those failures and failure modes? Okay, and that in a nutshell is what we're going to be doing. Okay, and there's a whole list of these sources that I've used later on in the presentation, so we'll talk about that as well. So who invented it? Well, FMEA was invented by the US military, and as far back as the 1940s. So we have there a reference for that. And it was a reliability evaluation technique. So as the name implies, it's focused on failures, okay, which is good in some ways, but of course it has its limitations, and we'll talk about those later. And as it says, it was one of the first systematic techniques. And I've got this quote from the ASEMS toolkit from the UK MOD, and I've got a PDF of that, which I will, you can go and look in the toolkit. There's lots of good stuff in there for free, but I've got a PDF download for you as well, which I'll share with everyone who's attended. I'll email that to you after the event. So what can FMEA be used for? Okay, so as I've said already, we can use it for looking at how do we get rid of process failures, or how do we get rid of product failures, or not necessarily how do we get rid of them, but maybe how do we mitigate them or prevent them from becoming an undesirable event. So we recognize we're never going to have perfect reliability. Some failures are inevitable, but maybe we can design or architect the system so that as few as those failures as possible actually become significant, as in interrupting the operation or the mission, or causing a safety problem. And as a safety engineer, I'm particularly interested in that. And as it says, again, this is a quote, FMEA is effective for both. We can apply it to an old system. Maybe we've got an existing system and we've had some unexpected failures or unexpected problems, and we want to understand why that's happening. Or we're using it for a new system in development. Okay, and again, we'll talk about that more in a moment. And as it says, for more processes, it can identify not just failures, but usability problems, potential bottlenecks, or unintended consequences. And this quote actually was taken from a medical focused publication, because FMEA seems to have been, from what I can see on the web, FMEA seems to have been adopted by the medical profession quite widely. It seems to be very, very popular. Excuse me. So it's being very widely used. Okay, so when should we apply FMEA? Now, here's an example in the green cloud over on the right-hand side of the V. Sorry, this is taken from ARP 4754A, which is a aviation safety standard. And here they are suggesting that we can use FMEA or FMES. So FMES is a failure modes effects summary. Okay, FMES is a variation on a FMEA with a very complex system like an aeroplane. So on a commercial aeroplane, you know, an airline or something like that, we're going to have tens of thousands of components. So our FMEAs on each system or subsystem, if we have them, could easily run to hundreds of pages. Okay, now, you know, generating and reviewing a FMEA of hundreds of pages is tedious, you know, as you would expect. So very often when we have such voluminous results, what we might do is have the, you know, we'll have the raw results, and then we'll boil them down maybe to a summary that does some trend analysis and pulls together maybe only the significant failures above a certain threshold that we're interested in, or maybe failures within a safety critical functional chain, something like that. Okay, so that's the purpose of a FMES, in order to make the information more manageable. Okay, because the sheer volume is a problem with FMEA. Now that's what it says in the standard. I personally don't think that's the only place you can use them. So in the standard, we're using it on the right hand side of the V. So we've completed software and hardware design, and we're now doing integration and testing and analysis. We're doing system safety assessment on the right hand side of the V. But actually, we can use a FMEA on the left hand side of the V as well. So we can do preliminary or predictive, if you like, SSA over on the left hand side. And maybe if we're considering new designs, or we're considering candidate architectures or designs, we could do a relatively high level FMEA to help us understand, what are the failures, what are significant. If we bought this subsystem or component or reuse this thing, what would be the significant failures that we would then have to manage? And therefore, what would be easiest to manage in our chosen architecture? Okay, so we can do some front end work with FMEA. Okay, it doesn't always have to be about generating hundreds of pages of tables after the event. Okay, yes, we need to do that to help us understand, reliability, mission failure rates, safety occurrence rates, that kind of thing. But we can also use it in design at the front end. Or even if we go back any further, FMEA is very closely related to functional failure analysis, and I've talked about that in a previous webinar. An FFA, we don't need a design at all. So we can do an FFA purely on requirements and said, well, if this function went wrong that we've specified that we want, or the customer said that they want, what could go wrong? Could it be hazardous? So we can take the FMEA family very, very early up the left-hand side of the V model, and apply it all the way through. Moving on. So where FMEA is used, and I've got a #1 on this because there's two meanings to this question in my view. So in terms of where it's used in industry, all over the place. Okay, as we've seen, there's lots of benefits for FMEA, and it's used in automotive, healthcare, aviation, basically anywhere where the consequences of failure can be unpleasant for people, harmful to people, or expensive. Okay, so anywhere where it's worth spending a little bit of money to understand what our failure modes are and what to do about them. Okay, so that's the first meaning of where. The other meaning of where I think that is helpful is what do we do with the data? Okay, and specifically here, I'm thinking, well, what do we do with the results of a FMEA in a system safety program? Okay, and typically we would use the FMEA to either just give us directly do the analysis to help us come up with hazards and controls, and we can do that. We can just take the tabulated data and go, right, we've identified some hazards, we've identified some failure modes that need to be managed, therefore we've identified some hazard controls. Okay, that's fantastic. We can do that. We can also use it as part of, as just one component of a wider system safety program. And in this case, on the illustration on the left, we might use the FMEA to generate the data that goes in at the bottom end of a fault tree analysis. Okay, so we're generating all of these failure modes, and then we are putting them together in order to see how they might combine in order to lead to a top event. Okay, and the top event might be an overall system failure, or it might be a hazard, depending on whether we're looking at reliability or safety. Okay, and so we would use the FMEA generated data to feed our fault tree, and indeed to help us construct our fault tree. So FMEA provides the causal data, tells us what the failures are. If we are putting numbers on it, maybe if we've got some data on component failure rates, we can put some numbers on that, some probabilities of failure. We can also, perhaps more significantly, talk about which failures matter. Okay, so if we then start to consider, well, what are the effects of this FMEA, and how critical are those effects? And once we start to consider the criticality, we have a FMECA. We've added in criticality to the FMEA. And it gets a bit sort of water is a bit muddy here. You know, on the one hand, we've got FFA, we've got different kinds of FMEA, and then we've got FMECA. They're all kind of the same family. It's a matter of of emphasis that we put on. How much effort do we want to go to? Do we want it to be qualitative or quantitative? There are lots and lots of decisions that we can make about how we use a FMEA and what we want it to do. But as it says, if we think about criticality, how likely are these failures? We can feed all of that information into the bottom of a fault tree, help us construct a complete fault tree, okay, where we've considered all significant failures. Clearly, if a failure doesn't propagate, it goes nowhere, it has no effect, maybe we're not so bothered about that. But for all things that could lead to a hazard or a potential loss of controllability, let's say, then we would want to include that in our fault trees, whether they be qualitative or quantitative. Okay. We don't always have to put numbers on fault trees to make them useful. So that's the, if you like, the second meaning, I think, of where FMEA is used. By the way, do please put any questions that you've got while we're going through in the chat. I can't actually see it while I'm presenting, but I will pick up your questions when we get to the Q&A session. So please go ahead and type your questions into the chat. Okay, so why FMEA is important? I think we probably covered this already. We've talked about the benefits. In fact, you've seen this quote a few slides back. There are lots of benefits potentially from using FMEA. It's quite a simple analysis, basically, and it's quite easy to understand. It's widely used and understood. You get some nice tabular output that is relatively easy to understand and review. So there's lots and lots of benefits, and it can do, significant things for us. And on the right-hand side here on the slide, we've got a slight variation. Some forms of FMEA, you can come up with what's called an RPN, where we can prioritize these failure modes and say, okay, we can score them on severity, how likely they are to occur or how frequently they occur, and can we detect them or not? Can we do anything about them? So clearly, if we've got a failure mode that could have a severe outcome, if it happens often and it's difficult to detect, well, that's really bad news, and we need to prioritize that and look at that in far more depth. So something like an RPN gives us a consistent scoring system in order to prioritize things. Okay, and you get the numbers that you get, as you can probably see. If you've got something that's highly significant, it's going to score in the tens to maybe up to even 100, as opposed to low-level things that might only score as a 1, 2, or 3. So it really does bring out the most significant failure modes and to help you prioritize them. Those are benefits. there are also downsides to FMEA. Okay, so first of all, as the name suggests, FMEA is focused on failures. Okay, now lots and lots of accidents occur when nothing has gone wrong. Okay, so FMEA isn't necessarily going to pick up something where the system or the process is working correctly, but there's been, the context or the system has prompted somebody into erroneous human behavior. Notice I don't say human error, erroneous human behavior. The human has made a mistake for whatever reason, under pressure, difficult circumstances, not a lot of time to make a decision, whatever it might be. But there are lots and lots of very significant and lethal accidents where the system has been working perfectly. Okay, and a FMEA won't pick up that kind of stuff. And in fact, people like Professor Nancy Leveson have criticized failure-based techniques and said we need to go much broader. We need to think about loss, not just about unreliability or failure. We need to think more widely about control. And so there are other techniques that will help us do that, which FMEA won't. The other thing with FMEA is on its own, it tends to focus on single failures. Okay, if we want to understand the consequences of multiple failures across a complex system, then we need to do our FMEA and then feed that information into constructing a fault tree. Okay, then the fault tree will allow us to look at failures at a low level and see in what circumstances individual failures could propagate up to become a hazard. Okay, so if we want to consider more than one failure, then we need to apply different techniques, be it let's say a fault tree or some other sort of common mode failure technique to complement the FMEA. Okay, so those are, it's a good simple technique. If you want to be more sophisticated, you've got to mix it in with other things. You need a bigger program, of which FMEA is only a part. So FMEA tools, basically I went on the web and looked up some that seem to be very popular and recommended by different people. I have not used these tools, so I'm not making a recommendation. I'm just pointing out there are a lot of tools out there. Okay. Now, significant, I think, to say, think about, there's lots of variations in FMEA. Think about what you're trying to achieve and therefore what kind of FMEA or FMECA or FFA you want to do. And then see whether the tool meets your requirements. Okay, so lots of decisions to be made about what kind of FMEA you will do, at what level, how much detail do you want to go into, or maybe you have to because the regulator says you does. So says you does, I do apologize, says you do. So maybe the regulator has made some of those decisions for you, but for most of us, we actually need to think about what we're going to do and pick a tool that supports our chosen process. Okay, so the tool really is the last choice. Now, what I would say on making all of these decisions, there are lots and lots of very good free guides and templates out there for different kinds of FMEA. We'll see an example in a minute. I've chosen quite a simple one. There's a slightly more sophisticated example in the PDF handout, but there's lots of other stuff out there. And if you follow some of the links that I've provided, you'll see them. Okay. So lots of good stuff out there. I'm not pushing, the example I'm showing you, I'm not pushing that as the only answer. It certainly is not. There's lots of good things out there. But as I say, process and good practice and involving the right people and getting the right information, these are, in my view, more important than the tools. The tools become necessary when we get into very large scale generation of Formica tables. When we're generating hundreds and hundreds of pages of output, tool support is vital. Okay, we can do it in a spreadsheet, as we will see, but maybe that's not really up to the job for, you know, for mega industrial scale work. Okay, so those were all the topics I wanted to cover. In order to go through that stuff, I've been on these sites, quality sites, Medicare, Safety Culture. So there's lots of good information there. And as you'll see, for example, on the third one down, there's a guidance PDF on that site at the cms.gov site. So that's good. And also, I'm going to be emailing you the PDF for the ASEMS Toolkit Guide. So if you prefer to read information in that format, if it's helpful for you to take that in, I will send that to you. It's also got some further links to standards. Okay, so if you want to follow a particular standard or you're required to, there are some examples there. There's lots out there, okay, different industries apply different standards. So it's just a short list, it's not exhaustive. I said I would share some resources with, in fact, I have shared some resources with you in the chat. So all of my webinars get recorded. I'm hoping this one is recorded okay. And they all go in my System Engineering Academy. And there's a link to that there. And you can, normally it's $45 US a month with 7 days trial period for free. But if you go to the follow the link, sorry, and apply the 1 month free code, you'll get a month and 7 days free. I think we'll see how it works. Certainly, you'll get a month free. There's also lots of information at my website, safetyartisan.com. Lots of free stuff there and downloads. If you want to keep up with the output that I'm producing, the content, do please subscribe. Click on the link to get regular emails and you'll get discounts and stuff. Make sure that you double select to say yes to the emails, otherwise you won't get anything. And do please check your junk mail. Okay. And so if you go to there, you'll get lots more information. And I've also got a ton of videos on my YouTube channel. And again, please go there and like and subscribe and follow. And you'll, every time I produce a new video, you'll get an update, which reminds me I've got a release. I've got a few in the pipeline, which I need to keep releasing. So there's some resources there from me to you, and that's all in the chat. And as I said, this is a series of webinars. This month we've done FMEA. Next month it's risk matrices. And I'm beginning to think about designing that. It might end up being 2 because there's so much material potentially, because I want to do some basic stuff on this is how you construct a risk matrix, because it's the decisions behind the matrix that are important. But also lately, there's been a lot of people having a go at risk matrices. There's been a lot of clickbait on LinkedIn and so forth about our risk matrices are rubbish, blah, 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 garbage. Don't believe a word of it. But I will maybe do a second session on problems with risk matrices and maybe how to overcome some of them. Okay, probably with a MIL standard 882 focus. Okay, because that matrix does have its problems. So that might be December or December and January. Then we've got risk registers and hazard logs, and I've done some sessions, a previous webinar on that, which is in the Safety Academy. What I'll do in January or February, probably look at a full function hazard log with you, and we can talk in more depth about what a hazard log or a risk register or a hazard tracking system can do for you. And then we've got more sessions: causal analysis, safety audits, HAZOP, event trees, claims, argument, evidence, and goal structuring notation, and fault trees. Okay, and these are all very, very popular topics, so I hope you will find them helpful and enjoy them. So that's what's coming up in this series of webinars, and I say they'll all go into the Safety Engineering Academy, where they'll be available to you. Okay, so that's the end of the presentation. I'm going to stop sharing now, and then we will, okay, we'll see what we've got in the chat. Okay, so we've had some messages there. Thank you very much. Have we got anything in the chat? Have we got any further questions, please? And just to let you know, there's the Restream video mechanism, magic, puts in a delay that may be up to 2 seconds between what I say and what you hear. So if I take a few seconds to respond, that's what it is. Do we have any questions, please? Okay, I'll give us a little more time in case people are frantically typing. All right, here we go. So, okay, level of FMEA, I use the system, component, and piece part levels. Is that consistent? Yeah, absolutely. So you could do it at quite a high level and produce quite a compact analysis, or you can go all the way down to piece part, down to component level. Of course, you'll get a lot more output if you do that. So yes, what you're saying is, I think we're talking about the same things. And Gil, states and modes. Right, so Gil or Jill, forgive me if I've got your pronounced your name wrong. So I think maybe you're referring to states and modes as you might see in a functional performance specification or something like that. So that I would say is more about the higher level states and modes of an overall system. You know, maybe it's in operating mode, and then you take it into, you know, you stop operating it and you put it in maintenance mode, or maybe you pack it up and do some maintenance on it to store it long term, let's say. So that might be storage mode or archival mode for an information system, let's say. So I think states and modes, we're talking much bigger handfuls, okay? And maybe for that kind of stuff, you would use a functional failure analysis, or you could use, if you're talking about a repairable system where you're looking at availability, you might use Markov chain analysis or something like that, rather than a FMEA. So lots of options there. Do come back to me if I've missed the point on that, by the way, Gil. Any advice on how to convince management that reliability helps with safety analysis when they push back on allocating resources? Okay, yes, you can do address safety and reliability at the same time-ish. Once you get into very detailed level, you've got to think about what criticality we're talking about. We'll talk about that in the example. So we might be thinking about reliability. We might be thinking about mission criticality. You know, is a failure going to take our system down and upset the customer? So that's a good way to get management attention. You know, the people who pay us are going to be upset if the system goes down. So we want to minimize that downtime, and we want to know, you know, if we understand why the downtime occurs, then maybe we can get the system back up more quickly, so we can maximize MTBF and minimize MTTR, to use the reliability terms. So we can do mission safety and reliability all at the same time. But yes, if you relate it back to how does it affect the customer, you know, who are presumably paying us or for providing a service, maybe that's the way to do it. As engineers, we love to dive down into detail, don't we? But that doesn't always appeal to management. So if we can talk in sort of client speak, we can think about who our system is, or a system or process is serving, and what the benefits are to the customer. Maybe that will help us with management. The other way I think maybe with management is, if you start off at a very high level, do a fairly crude analysis and demonstrate, look, we've identified some things. Most stuff maybe doesn't matter, but we've identified some things that really do matter, and then we've prioritized effort only in those areas. Maybe that's a way to convince management this is a way to save money in the long term by focusing our efforts. So I hope that was helpful, Brad. I think I'll be putting all of this in FAQ. Oh, you're welcome, Jill. And Brad, you're welcome. Any more questions? We've got plenty of time, so if you have any more questions, do go ahead. Okay. Well, I think we will move across and we will do a little example. So I'm going to share. Okay, so we should all see a little table here, and we'll move to the right and I'll show you the example. But it's a brake on a vehicle. So here's a little example for me, a table, and I just took this format of, one of the first results off the web. So basically in our columns, we've got a numbering system, which we're going to need when we've got a lot of output. We've got a description of the item that we're considering. So we're considering a physical system. So we're breaking it down into items or components. What is the function of the item? What does it do? What's our failure mode? Identification number. Again, when we have lots of output, we'll need this. What's the failure mode? And what are the effects, both immediately, higher up, and maybe end effects. And end effects is where, it's beginning to impact the user, the customer. This is the stuff that management will find significant. Now, strictly speaking, this is actually a Formica table, because on this table we can assign a severity, and in this case, severity 1 is we could hurt somebody, or it's critical or catastrophic, and severity 4 is no effect whatsoever. Okay, I'm not going to bother filling that in. Well, we might do. We'll see how we go. And then we got some additional columns here. So in fact, we could do a Formica, or FORMIA, sorry, with just columns A to F. Okay, that would be a very, very simple FORMIA. And then we are maybe adding the criticality considerations here in columns G to I. And then finally, when we talk about detection and mitigation, we are anticipating some controls here, either from a perspective of reliability or safety. I'm going to focus on safety. And then remarks, maybe we're going to put some amplifying remarks in there. Or if we got a bunch of people, we might allocate an action to an individual in that column. So there is our table, and I've got just a couple of examples. So what we're looking at, and it is a very simple example, quite deliberately. Now, why is that? I don't know if you're seeing a hole in your diagram as I am. I don't know why that's happened. Never mind. So here we got is a very old-fashioned drum brake, and basically, for those of you who aren't as old as I am, a drum brake is an old-fashioned braking system. Almost everybody uses discs these days, except on bicycles. Well, even they use discs. So what we've got an expander at the top here, And the expander is usually some kind of hydraulic piston where fluid gets pumped into the piston, and the piston forces apart these semicircular brake shoes. Okay, so these brake shoes are then have got the purple material here. It would have been asbestos or something like that years ago, but there's some sort of ablative material that gets forced against the brake drum, and when the brake drum is attached to the wheel of the car, and so that decelerates the car. So by applying by squeezing the brake shoes and the brake linings onto the drum, we get friction and we get deceleration. Okay, so the shoes are forced apart by the expander at the top. The shoes pivot at the bottom on the fulcrum there, which we can adjust. So if we got brake wear, we can adjust the shoes to make sure that they make good contact. Okay, so there's an anchorage point down here. That is basically a brake drum. It's very simple. And then finally, the retractor spring. When we release the pressure on the brake shoe, when the piston contracts again, the return spring just makes sure that the shoes come off the brake drum and the braking effect ceases. And that is basically the operation of a brake. So I'm going to go through this in front of you. Okay, so first of all, we've got our expander, our hydraulic piston up here. So what happens if, and the expander, the function of it is to push the brake shoe against the brake drum. So our first failure mode is no hydraulic pressure. So we're not getting any pressure to the expander. So the immediate effect would be, no expansion. Oops. This is where you discover that I can't spell or add up while people are looking at me. So no expansion, let's say, of brake shoes. So actually, maybe just say no movement. Okay, so by the way, it's perfectly normal as we go through this stuff. The reason I'm doing this live, I haven't, as you'll see, I haven't rehearsed this particularly well. It's okay to make mistakes. It's okay to go through, and then sometimes you'll get part way through and you'll suddenly think, oh, I've misdescribed the function, or I've got the failure mode slightly wrong. So as you go through this, you will refine your assumptions, okay? And you realize you hadn't understood things as precisely as you could. So no movement of brake shoes means no pressure against brake drum. And apologies if this is a bit simple. So no braking. Okay, which is obviously a bad thing. We've got our brakes have failed. Let's just sort that. Yeah. So now I'm guessing if our brakes have failed, well, there's an issue here. This is just one brake. Now, if the hydraulic pressure, if it's one system, so all four wheels on the car, then that's, that's a critical or maybe even a catastrophic failure. Oh, I do wish I could type. There we go. So it would be severity 1 if we've only got one brake circuit and it's failed. Okay, now we can begin to see probably we wouldn't do that. We would have two circuits on, on diagonally opposed wheels. Of course we would. Why wouldn't we? So even if one circuit fails, the other one, we've still got partial braking. And because we've put them on diagonally opposed wheels, we won't get swerving. Okay, so that, I mean, it's still undesirable because we've got reduced braking capacity. So then that might become, let's say, that might knock down a severity to severity 2, let's say, if we have that. And what's the detection? Okay, so maybe if we've got a pressure sensor in the hydraulic circuit, circuit triggers warning light to driver saying your brakes have failed, or half your brakes have failed. Okay, so there we go. There's just one line, and we've actually, not only have we looked at the failure, we've actually come up with some really useful information. Okay, I know it's a very simple example and it's very old tech. Okay, so let's move on. I will just do another 5 minutes of 10 minutes of this, and we'll have a few more minutes for more questions. Piston leaks. Okay, so if we've got no pressure, we could potentially, well, we might have reduced pressure if we're still getting some pressure. So I tell you what, let's copy this down there. So instead of no movement, let's be reduced movement of brake shoes. Instead of no pressure, whoops, reduced pressure against brake drum and reduced braking. Now, having said that, if we've got a leaky system, eventually we're going to lose all pressure. So reduced braking, okay, we've said, we'll say severity 2, because we've said severity 2 here for reduced braking. Okay, detection, yeah, maybe pressure sensor. If the pressure sensor detects it's beginning to drop, okay, same mitigation, probably. Again, if we got two circuits, okay, maybe that remarks thing from the no isn't as relevant, but it might be. So we're beginning to see here already how repetitive these things can be, which makes it easier to fill in the table quickly. But of course, if we go too quickly, then we can make mistakes, particularly when you're talking about huge tables of data, which maybe you've worked on over a long period of time. So piston sticks closed. Okay, so that means that the piston, the expander, is not going to move at all. It's not going to expand the brakes, which means no braking. Okay, so let's just copy all of that for now, because we've got no braking at all. So let's just check this. No movement against brake, no pressure against brake drum, no braking. Okay, agreed. Category 1. Now, no, hold on, but it's only one piston. Okay, it's only one piston. So if it's just one failure, we've still got so one piston per wheel. So there's an assumption there that I'm making. Whoops. So we've still got 3 out of 4 brakes working. Although we are going to get a bit of swerving though, aren't we? So maybe that is category 2 again. So, whoops. Yes, swerving while braking. We might have that. So pressure sensor isn't going to do anything for us in this case. So maybe something more sophisticated that can maybe tell that the piston hasn't moved. So that's not static, is it? We might sense from some kind of the way the hydraulic pressure responds to a braking command that there's something wrong downstream, but that's a lot more sophisticated, isn't it? 2 circuits isn't really going to do anything unless we detect a failure on one circuit and then disable the opposite wheel brake as well, which again requires something much more sophisticated. Yeah, maybe we'll delete that. Not sure. Not sure if we can. If you're sat there, by the way, thinking you know the answer, I do apologize, but that's not the point of what we're doing. Piston sticks open. Okay, so we now get no movement of brake shoes, but what we get is we get pressure against the brake drum when not required, which means we get uncommanded braking. Okay, so again, we can see some similarities with a functional failure analysis here. Now, uncommanded braking shouldn't be as bad as no brakes because people should be leaving a safe distance behind us. So if we suddenly get uncommanded braking, it shouldn't be as bad because the person behind, and if there is a car behind, should have enough space to stop. I mean, we all know that that doesn't always happen, but anyway, or maybe they can avoid us. Yeah, sorry, I don't know what a Poseidon is. It sounds, we could have an interesting there. So uncommanded braking, so detection. So if the brakes suddenly come on, we will get, or driver should notice and swerving. Although if we're talking about, let's say, a big truck that's got loads and loads of wheels, then maybe one brake coming on won't be quite as noticeable. So again, we're making assumptions about the context, which can change everything. Okay, so mitigation. Okay, could we have, you know, is there a fail-safe position for the piston? Now, probably we would want, we probably wouldn't want the piston to fail totally. Maybe we could have dual pistons per wheel. Okay. And in actual fact, of course, dual pistons per wheel, we could have that. We could have that for the one above, couldn't we? So I will just add that. There we go. So I'm just going to There we go. I'm just going to adjust this slightly. So here we go. We've done just one component, the brake piston or expander. Okay. And that's, what's that taken? 10, 15 minutes, if that. And we've learned quite a lot. We've come up with quite a lot of ideas for detection and mitigation, albeit, okay, you know, we're familiar with cars, so we're probably aware of all of these things already, but you know, it's an artificially simple example. So we can see how powerful this approach is. And, you know, we could go through all of this for the brake shoes, for every component in the brakes. And we can not only understand the failures at this level, at the level of the brake or the wheel, we can appreciate the effects at a higher level, and also what we might do about it at an architecture level above the level of the wheel brake itself. So we've got quite a powerful technique here for getting results quite quickly. And, you know, as we've said before, we can apply these techniques to lots and lots of different things, to processes. We could have a process flow diagram here, etc. Mind you, if we've got a process flow diagram, you could argue we should be using a HAZOP, but that's for another day. Okay, so I'm just going to stop sharing and go back to and see, have we got any additional questions? So thank you, Matthew. Is there merit in performing a root cause analysis? How do we, yeah, okay, yeah, fair enough. That, I would suggest, depends on the complexity of our system. Yeah, the simple one we've done there, yes, it's relatively easy for us to work out what's going on. And indeed, we could do a simple FMEA on the hoof and help us to work to understand the architecture. But yes, if you've got a much more complex system that's already designed, then you might well need to do some analysis to understand what you've got before you can actually construct your FMEA table. Whether that's root cause, or maybe you go down to, you know, you break your complex system down to subsystems and says, what function does it provide? Then we're getting more into FFA. So sorry, I can't give you a hard and fast answer, Matthew. It all depends on what we're doing. I don't think I've ever done that root cause analysis before, FMEA, but that doesn't mean that it hasn't been done in results that I've reviewed. Okay, excuse me, that was a suspected spam caller. Any more questions? We're out of time now, so if you've got any more questions, do please go onto the Academy and ask me some questions on there, and we'll answer them subsequently, or send me an email, or, you know, drop me a line on the website, or whatever it might be. Okay, so thanks very much, everyone, and I'm gonna drop off now. As I say, do keep those questions coming, and thanks very much for your input today. All right, thanks, Matthew. Okay, thanks, everyone. Bye-bye.